Hi, this is Shelley Physics, episode on work and the work kinetic energy theorem. This lesson starts out with work and energy, and later on in this course, we're going to be looking at momentum and impulse. And these are a couple of new concepts that are like an addition to Newton's second law. It's an extension. These are excellent tools that can be used in various situations, but it's just an extension of Newton's second law and third law in some cases. So with work, we actually start with the stuff we've been doing. We're going to start with a force diagram. I want to introduce work in this way. So here's just a scenario here. We've got some kind of object that's going to be slid across a frictionless surface. Call it a box that we're moving. So we've got to move this box around. There's going to be a force applied, and we're just going to say it's at an angle, because when you push a box, you usually don't get down on the floor and push horizontally. So you usually push it at an angle. And we're going to slide along the floor with some sort of displacement. We'll call it delta x. Displacement delta x. All right, that's it. So what we do in this last unit, we draw a force diagram. There's the mass of the box. It has a weight to it. There's this force pushing at an angle. I'm going to draw it from the object down. So there's the force. And you see this angle right here is going to be actually from this reference over here. And of course, there's going to be a normal force. Now, this force is pushing down and over. So in addition to the weight, the normal force the floor has to support a downward component of this force F. So the normal force should look, when we draw it, a bit longer than the weight. That's going to incorporate the downward component of the force and the weight together. And that's it. That's our force diagram. Now we're going to separate that angled force into its components. We're going to keep the normal force in the y direction. The acceleration of this box is going to be to the right. So we want to make sure the right stays as our x-axis. So I'm not changing the orientation here to suit F. Now this force F has a right-hand component and a downward component. And the side adjacent to the angle here is the horizontal side. So this is going to be the cosine, F cosine theta. And that makes this component down here the F sine theta. Hopefully this is nothing new. Should look familiar at least. Maybe you haven't seen this particular situation yet. All right, so what's the acceleration of the block going to be? We're going to solve for acceleration with net force equals mass times acceleration. We're just looking at the x direction right now. Okay, and in the x direction, the only force here is F cosine theta. And that gives us a mass times acceleration. Now, in the y direction, just important to note here, because if friction is involved, normal force is going to be helpful to know something a little something about. So let's just solve that y direction here before I move on to get to work. Before I get to work. And in the y direction, we're going to have the normal force up minus the weight down minus F sine theta. You see there's a component of that pushing force that's going to be involved in the normal force here. It's not just going to be mg. Well, let's note that the y direction acceleration is going to be 0. We're pushing down into the floor, so that's not going to accelerate downward. The floor is going to increase its normal force until it balances out the weight and that component. So the y direction acceleration is 0 there. And we'd end up with, if we substitute mg for fg, we'd end up with the normal force being equal to, if we add mg to the other side, to the 0 and f sine theta, we'd end up with an mg plus f sine theta over there. And you'll take a note here that if the angle of the floor, or angle of the push is 0, if we're pushing horizontally, then the normal force is equal to the weight, because sine of 0 is 0. That would cancel out this term. So that's just a curiosity that might be important if you get friction involved, because friction is mu times normal force. All right, and we might come back to that later. Oh, sorry about that. That's equal to friction. There we go, if you can't see that off the screen. All right, getting back to this x direction. Now, at this point, if we were to look for A isn't very easily obtainable, measurable. There are things called accelerometers. You'll find one in your cell phone, but they're, measuring acceleration isn't always the easiest thing to do. And working with velocities is a lot better. Often with vehicles or cars, you've got a speedometer, so you can read your magnitude of your velocity right off your dashboard. So what if we turn this into this acceleration? This is where the tool aspect comes in, where work comes from as a helpful tool. We're going to use velocity instead of acceleration as a more helpful quantity. And also, we've got a displacement that's measured. You'll notice I haven't mentioned anything about time yet. Like, but time's not really important here. What if we're just moving a box across a room a certain position, a certain displacement here? It takes work to do that. So we should get a quantity out of all this, what I'm about to do, called work. And it is a physical quantity. Whenever you do work, you move something, you have to apply a force and you shift that something's position. When you do work out, the something you're moving is yourself, or it could be weights that you're lifting. So think about running. What work are you doing there? Well, you are kind of pushing yourself sideways. It takes a little bit of work, but every time you take a step, you're actually lifting your center of mass up and letting it fall back down. So when you take that step forward, your body falls down a little bit. Go ahead and try it. Get up and feel this. Get up out of your seat if you're sitting down. Take a step forward slowly, and you'll feel your body kind of fall down, because when your legs are like this, you're a little bit lower than when your legs are straight up. Okay, straight up and down. So when you take a step forward, you have to fall forward, and then when you crisscross your other foot over, you lift up a little bit before you fall back down. I don't know if that's a great illustration, but thing I like to do whenever I'm just kind of bored waiting for someone at a store in the mall, just kind of look out over the heads of people. You're just kind of sitting and you're looking at this busy crowd walking along. Or if you've ever seen a video of New York City streets, I love New York City. If you're walking along, you got all these people walking. They walk everywhere. They're very fit people up there in New York City. They're walking along everywhere, and you just kind of look at their tops of their heads, and I can, because I'm a taller person, you can kind of see the tops of people's heads. It's one of the advantages. The disadvantage, though, is you clunk your head a lot on things like hanging lights and low objects and cabinets. Man, I got a lot of issues up there. Anyway, besides just physical, little mental issues too. Back to the city streets, you can see the people's heads bobbing up and down, because when they walk, they're lifting their body up just a little bit and falling back down. So when you do a running workout, you are lifting your body up and down. You're lifting it up and letting it fall back down over and over again, and that's the workout. Of course, lifting weights, there's a workout there. You can also push things side to side here if you're overcoming friction. So any work involves displacing an object, whether that object's external to you or if it's you yourself. You can also run upstairs. That's lifting you up. That's a workout. So where does work come from? Let's get acceleration in terms of a change in velocity, or initial velocity, a final velocity, and displacement. Might refer back to acceleration. What's a linear motion equation for acceleration? Let's say average acceleration, where time is not a variable, and that one would be this creature here, the 2a delta x. We get the delta x involved there, and that's final velocity squared equals initial velocity squared plus. So if you recall this equation of straight line motion, we start with that one, but let's rearrange it. Let's solve for acceleration. If we subtract initial velocity from both sides, we end up with a final velocity squared minus initial velocity squared, and then divide by 2 delta x, and that will give us the acceleration. All right, so it seems like I'm making this a little bit more complicated, but it's for a good reason. These are more measurable, useful things, and they're quantities that are involved in this scenario. So we plug acceleration in down here. I'm just going to redo that because that's a funky F. We're going to plug acceleration in down there. F cosine theta equals m, and then we got a VF squared minus V initial squared over 2A delta X. Okay. I just got an m hanging out in front here, so I don't really need the parentheses. Let's pull some of the stuff out. First, I'm going to multiply. We've got a force and a displacement up here. These are the givens and a theta. So I'm going to put all those givens on one side of the equation. I'm going to multiply both sides by delta x. Okay, and that cancels out the delta x over here, and we're going to end up with a f delta x cosine theta. We're putting the thetas on the end there. Equals. Okay, what's all this stuff here? We've got a. Well, first I'm going to factor out this 2a. Just pull that out of the expression. Whole bunch of algebra here. That's all it is. And okay, this side remains the same. F delta x cosine theta. Now, just to clean this up a little bit, we're gonna distribute here. I'm gonna. Shelly, you did it again. I make mistakes for you. I substitute for a. So I get used to writing 2ax all the time here. So apologize for that. Okay. So I end up writing 2ax right up there. Anyhow, there should not be a 2ax. We're substituting for a. There's only a 2 delta x down here. So there we go. It's going, wait a second, that a shouldn't be there. All right, so the a is not in there. And so get back to it. We have a 1/2 m. I'm going to write it like that instead. 1/2 m. And distribute that 1/2 m to the VF squared. And then we got a minus 1/2 m V initial squared. All right. Now this expression is important. And that's what we're going to come back to. Let's talk about what we've got here. What is this creature I have created? This is called the work kinetic energy theorem. So you might be asking, where is work and what the heck is kinetic energy? Well, on one side, this is an expression that's called work. And over here, this is do you notice it's a change? It's a final condition minus initial. This is a change in something called kinetic energy. So this is work equals a change in kinetic energy. And this is our key expression. What's going on? Well, first off, let's talk about work, because that's what this whole lesson is about. We've got this force times displacement cosine theta. What kind of quantities exactly are force and displacement? They're vectors. Do you remember that? Force has a direction. Displacement has a direction. Do you see they both have arrows? There's directions to these. So they're both vectors, and we're ending up with like F delta x cosine theta. With that in context, is that ringing a bell? The magnitude of one vector times the magnitude of another times the cosine of theta. You know, isn't that a product? Okay, isn't that a multiple? So we have here an F dot x, force times a displacement. Okay, x is a displacement here, or change of position. I use vector x here. And if you recall, vector a dot b equals magnitude a times b times cosine theta. So out of this, we get an F magnitude of x, or F, times the magnitude of x cosine theta. That's the definition of a dot product. I'm looking at the dot product because there's a cosine theta here. So if you recall something about the dot product, it's also called the scalar product. This is a scalar quantity. Work is a scalar quantity. It's a scalar. Okay? Not a vector. And does that make sense on the other side? Over here, let's see, the 1/2 is a scalar. The mass is a scalar. Mass has no direction. And wait, velocity is a vector. But look at what's happening here. Velocity squared. We're taking a vector times a vector. Now, if we took the cross product or the vector product of velocity cross velocity, they're in the same direction. They have no perpendicular component to one another because they're the same value. So if we crossed the product of two of the same velocities that had the same direction, you get 0. That would be very unuseful. But if you take the dot product, the scalar product of velocity times velocity, you just get the velocity squared, whatever the magnitude of velocity was, squared. So the left side and the right side, these are both scalars. If we back it up to here, just think about our original velocity equation. Have you noticed that if you do square the final velocity here, you would also get a scalar value out of it? We've also got a vector times a vector over here on this side. That would also have to be a scalar. If you were actually like plugging in initial velocity in a kinematics problem, plug in acceleration and displacement. If you solve for the final velocity of an object that's accelerated over a distance, you'd have to square root both sides in the end. And what happens when you take the square root of something? The result is always plus or minus some kind of value. Do you see that in this expression there is no direction? It's lost. The direction is lost. You have to say it's either a positive velocity or a negative velocity as a result. So everything's pointing to work being a scalar. And getting back to what this is over here, this is a definition of kinetic energy. And we have to give some kind of units to all this. Well, the unit for work over here is a Newton times a meter. Now later on in this course, you're going to see another unit that's in a Newton times a meter, and it's from torque. It's from forcing an object to spin with a circular motion or move with a circular motion. And that'll have units of Newton meters. But that quantity is a vector. It's a vector quantity, and we'll get to that one later. But this one, let's focus on this, is in Newton meters, and that's what we're going to define as the joule. Okay, that's the unit for work. It's also the unit for energy, joules. Newton meters is joules. So this is our unit for work and energy. So if you can find the work done to an object and you know the mass and initial velocity, you can easily determine the final velocity. That's one little aspect of this work kinetic energy theorem. But it has a lot of other implications too, because we're going to look at different kind of forces. This is just talking about a force that's accelerating an object. What about forces that try to slow objects down, or forces that lift things up? We're going to look at weight, how weight's involved with force and work. Weight is a force. How weight's involved with changing kinetic energy. And we're also going to introduce potential energy, because some forces that are out there are conservative forces like gravity. I'll talk about what that means in a different lesson, or maybe this lesson later on. Okay, so let's go to a different scenario. What if friction is involved? How does this work out? How does this work out? Killing myself. Let's give a little angle here. Let's give it a 30 degrees. That one's easy to work with usually. I said it again, work with. Okay, and we got force equals. Let's give it a force of 50 newtons. See an example here. All right, and we're going to have a displacement of the box. We're going to go, let's go about 4 meters. All right, now I'm going to throw in a little piece here. The mu. This is a crate on a warehouse floor. The mu between that smooth warehouse floor and the crate is 0.40. All right, so My questions are, what's the work done on this box, on this crate, and what will be the final velocity if it starts at rest? And this is a very lightweight crate, so we're going to say this is a 2 kilogram crate. We need some mass in there. Okay, so that's our scenario. We got a box, we're moving it, and we got some friction here. What's up with that? Now let's keep in mind that work is F dot X. That is a mighty vector symbol right there. And that's the same as F times displacement. That's the amount of the displacement, cosine theta. And just to bring in the kinetic energy theorem, we've got a big old, this is equal to that is equal to that. And we need a minus. It's a change in kinetic energy. I did a plus there. Sometimes people make that mistake, and I almost did. Okay. So what's the work done? Well, what's given here, if we're to find the work done, I look at this scenario, it's not giving me a final velocity. So one way you could find work is if you did have the initial and final velocity. You'll notice that if you find the change in kinetic energy, that's also equal to the amount of work done. But in this case, what we have is a force and a displacement and an angle, and that's also equal to the amount of work done. And later on, this is how we're going to determine the final velocity. We're going to say that that work done is also equal to the change in kinetic energy. So you got all these things equal to each other. Just keep them in mind. You'll be able to use them in different scenarios. Sometimes you'll have an IJK notation version of force and displacement. You can use that in that case. Okay, you can use the dot product. So what's the work done? We're going to plug in the force, 50 newtons, times the displacement of 4, times the cosine of the angle. And that angle is 30 degrees. I should have used 60. That would have been easier here. So we got 50 times 4 is 200, and just multiply that by cos 30. And it's 173.2. Looks like I got 2 sig figs, so I'm just going to say 170 joules. All right, is that it? No. You see, there's this other thing called friction. That's at the work here. All right, so friction is at work. So this is the work done by the push. It's the work done by the push. And what about the work done by friction? Friction's another force. What's the work done by friction? Well, friction as a force is mu times normal force. Okay, mu times normal force. So that's the force. The displacement is 4 meters. So we do know that. And the angle, okay, well, let's see. What's the angle of displacement here? Well, the angle between displacement and friction is, well, friction's kind of going back this way, right? Let's label that force. It's going backwards. The displacement is forward. So with a backwards friction and a forward displacement, the angle between those two angles is 180 degrees. Okay, that's bizarre. So we got a few weird things happening here. Friction, what are you doing to us? Well, first we got the mu. I know the mu is 0.4. What's the normal force? Wait a second. Told you this would come up. I remember this guy down here. The normal force. We already saw this situation in the y direction. But just if you think about this scenario, there's the weight going down is equal to normal force usually, but there's a downward component to F. So the normal force is mg plus F sine theta. Let's just bring that in there. So our new work from friction is I already had it up here, 0.4 times mg, so 2 times 9.8, there's the weight, times the F sine theta. I'm sorry, so it's mg plus F sine theta, 50 sine of 30 degrees. Now normally you just kind of plug in the normal force there if it were a horizontal force. Usually normal force is just equal to weight. So that would normally be kind of easy there. And then we'd have at the end, so this is mu times the normal force times 4 cosine 180. I'm running out of room here a little bit, so I'm just going to try to drag this stuff over. More complicated than it should be. All right. So mu times our mighty normal force times 4, don't forget all this stuff, cosine 180. All right, so what is all this stuff? Let's multiply it out. Now cosine 180, you'll know is -1. So that's making this a negative work. What is that? Does that mean it's the backward direction? No. Remember, work is a scalar. This is a negative amount, not a vector. Anyhow, I'll do the calculation here. 0.4 times 4 times the quantity, 2 times 9.8 plus 50 sine 30 is 25. And it's 71.36. So I'm going to, at 71.36, 2 sig figs is, I'll just call it -71 joules. So we got the work done by the push is 170 joules. The work done by friction is -71. So the total work done by these two forces is 170 minus plus a -71. We're adding the amount of work from each of those, and we get 99 joules. That's it. The total work is 99 joules. Now to finish this up, that 99 joules is equal to the kinetic energy. So work is equal to a change in kinetic energy. And that's the piece we're gonna finish this up on. 99 equals 1/2 mv squared, mv final squared. I'm pulling off this creature right here. All right, the mass is 2. That makes it easy, kinda. Vf squared minus 1/2 times the mass times the initial velocity squared, 0. There it is. All right, so we got 99 equals half of 2 is 1 equals Vf squared. Our final velocity is going to be about the square root of 99, which is going to be about 10 meters per second. There it is. So work is a great tool. We figured out just from a displacement and a force, we're not involving time here. So you might notice without that time issue, there's no vectors that we got to work with. But the one little thing here is you got to consider all the forces in each of their individual angles. The work from the push was determined by this 30-degree angle. The work from friction is determined by, friction is backwards as the thing's being pushed forward. So what's that mean? If I'm pushing forward, my body, my arms are doing positive work to that box. But as I do that, friction is a negative force, so it's doing negative work. I'm trying to add kinetic energy, but friction takes that kinetic energy away. Guess what? Friction is the floor against the floor that heats up the floor, that creates kinetic energy in the floor. Energy is not lost in this system. It is dispersed in different parts of it, but it is not lost in the system. It's not destroyed. So we're seeing something called the law of conservation of energy at work here. In our next scenario, we're going to look at lifting things up. So here's a box again. We're going to lift it up this time. So there's going to be an upward pull or push. And of course there's a downward weight. Now that the upward pull is going to be greater than the weight. So here's the workout. We're going to lift things up here. And so what's the work done? What's the total work done here? We've got two forces. So we're going to have the work done by F, that lifting force, and we're going to add to that the work done by the weight. Might be kind of interesting to think about here. Work is done by gravity as we lift something up. All right, let's see if that makes sense later on. So work done by that force F. Let's give it some values here. Let's take a 2 kilogram box again, and we'll do again a 50 Newton force lifting it up. All right. So the work done by this, we're going to displace it up. We're going to lift it up a certain delta y. Let's use y this time. Now we'll lift it up 5 meters. Get a few different numbers here. All right, so what's the work done lifting this box up 5 meters? We're going to take work equals a change in kinetic energy, and keep in mind that work is F delta x will be delta y in this case, cosine theta, equals a change in kinetic energy, mvf final squared minus mv 1/2 mv initial squared. There we go. All right, just so those are reminders, nothing too fancy here. So what's the work done by F? Well, it's 50 is the force, and the delta y here is 5. So we're going to multiply that by 5. And how about the angle? The angle between the displacement delta y and F, they're both in the same direction. So this is a 0 degree angle. Cosine of 0. And cosine of 0 is 1, so all we have is 5 times 5 is 25, with an extra 0 is 250 joules of lift. All right. So there we go. And what about the weight? All right, let's check that out. What's the work done by the weight force there? Well, that'll be mg times 5 cosine of, oh wait, the weight force is opposite. It's in the opposite direction as the lift. So that would be a 180 again. This is going to be a negative work done. So cosine 180, that's -1. Mg times 5, let's see, m is 2. So that'll be 2 times 9.8 times 5. And that's with the cosine 180, that's a -1. So bring that over there, a little negative. So here we're going to get 19.6 times 5. Let's see. Well, that's 2 times 5. Okay, 2 times 5. I'll just do that. It's a little easier. 2 times 5 times 9.8 is -98 joules. Okay, so what's happening here is we lift this thing up just 5 meters. That's 250 joules of positive work done by that force upwards, plus -98 joules from weight. Weight takes that energy out of it. All right, and of course, you know what will happen next. We'll have well, that'll be a 152 joules of net work. How's that for networking? So what's that mean? That means this object's going to be flying upwards, but it's not going to be moving up as quickly as it would if I shove this with 50 newtons of force on a frictionless surface. If that were the case, it would be moving a little bit faster with 250 joules of kinetic energy. Now it's only 152. So what happens if we do work to lift this 2 kilogram block up 5 meters and it just stops at the top? So that happens all the time. You take objects and you lift them up. I mean, when you do a workout, you're not taking barbells and like throwing them up into the air like that. Okay, you're just lifting them up just a little bit and you let them back down. Lift up and let it back down. So the final velocity at the top is 0, just like the initial velocity at the bottom. So whatever work you do in lifting those barbells up, what does gravity do? It's got to do some negative work. So what's that going to look like? If we find the new situation here, what's the total work done by lifting a force up, lifting up with a force? What's the total work done in lifting an object up? Well, that's the lift force plus the work done by gravity. So the work done by lifting it through the lift force plus the work done by gravity. That would be the total force there. And in this scenario, the change of kinetic energy is going to be 0 because we're going to lift up that object and let it come to a rest up top. We're not going to go tossing it up into the air with this extra bit of energy. Okay, notice, remember, over here we had more energy than the weight force. But what if we're lifting up so that the change of kinetic energy is 0? So the final velocity is 0 and the initial velocity is 0. Now the velocity in the middle might be positive because we're moving at kind of a constant speed upwards, but we're going to let that gravity do its job and slow the object back down. So it's not a very quick motion, it's very slow. The big point here is that the total work done should be equal to 0 if we get a change in kinetic energy of 0. So let's see, how's the lift force, the work done by lift, how's that going to compare to the work done by weight? If I subtract this to the other side, this is telling us that the work that it takes to lift is the negative of the work done by weight. So if lifting this box up, this 2 kilogram box up 5 meters, gives us a work done by weight of negative 98 newtons. Negative 98 newtons. That means the work in lifting is a positive 98 newtons. Let's get that on the screen there. Okay, so the weight work is negative 98, and that means the lifting work is positive 98. So if we put 98 newtons of work into this, how much work does gravity do? Negative 98. It's slowed it down. It's at rest. When you walk up the stairs, you don't get to the top and go flying off into the sky. You're stopped. Every time you lift your body up one step and then another, you come to a stop. Your legs are doing positive work to your body, but that gravity is at the same time doing negative work to slow you back down. So that your total change in kinetic energy is 0 from the beginning of the step to the top of the step. So that's lift. You get the weight involved. So questions always come up oftentimes in physics. If this mass is lifted this far in the air, how much work does the lifting force do? And so you take the weight times the height, the change in y. Okay, and that's the work done by the lifting force. You're overcoming your weight. But then a question might ask, how much work does gravity do? That would be negative, the negative of that amount, negative mg times the change in y. And that's, if you see, that's what we've got right up here, mg times the delta y. All right, so that's work done in lifting. Here's our last scenario. It's a mass on the end of a spring. Now we do need to give the mass a value here, and the spring also has a property, that the spring constant, if you recall that, we're going to take a spring constant of 20 newtons per meter on the frictionless surface. We'll also say it's a frictionless surface. So remember, this is called the spring constant. There we go. And that means we're going to have to unpack Hooke's law. If you recall Hooke's law, let's say the magnitude of the spring force is kx. Of course, the direction there, if we make this a vector, where that looks like my g, there, that's a spring. Force of a spring is kx. So the Hooke's law says there's a negative on here. That means if we pull the spring outward one way, the spring pulls in the opposite direction the other way. So here's our kx, and more specifically, I should make this you know what? Here we go. Let's make this real clear here. Is a k delta x, because it's the displacement of that spring is what makes that spring have a force. Now, what's unique and different to this situation is that we don't have a constant force here. As the spring compresses and pulls that mass toward the right side this way, the x value is going to change. It's going to decrease. That means the spring force is going to decrease. We don't have a constant force here. What's that mean when we're looking at this creature here? We've been working with F delta X cosine theta. All right, what's that mean that's going to happen here? Well, this delta X is, you know, we can call it 2 meters if you want. Okay, it's an actual value, but as the X changes, the force is going to change. So what is different here is that this work depends on a force that's a function of displacement. So we've got an F of X happening here. And since this is a changing force, it's not a constant, that means this delta X, we've got to stop looking at like just a large change in position, but we need to add up the little pieces of work over small displacements as this spring compresses from, you know, its stretched out position to where it's going to go. Why don't we use a delta X of 2 meters here? We're using 2 meters before, let's use 2 meters here. So as this compresses from like 2 meters out to maybe its rest position, the spring's rest state of 0, the force is going to change. So this delta X becomes small little pieces dx, and we're going to add up all those little f of x times dx's. What this is indicating is this is an integral, and if we were to plot out force of the spring versus its displacement from its rest position, rest state, if you recall what that looks like, you're going to get some kind of straight line, and this gives us the, of course, the equation Fs equals kx, and that's always the magnitude, not the direction on this plot. Okay, and the slope would be the k value. The rise over run is what the spring constant is. Okay, so m is not mass, it's the slope here. I'm just trying to indicate that k is the slope value. So that's where we're getting this equation from. If this is the force versus displacement graph, you'll notice from this that integrating f of x dx will give us the area underneath of this curve. Now, if this position right here is 2 meters, then what we'd be looking for is the area under this curve. If you look at what we're just doing in previous examples, we had a constant force. So what if instead of being a changing force, what if the spring force were constant? Let's say a constant 20 newtons or something like that. Okay, then over that 2 meters of distance, we'd multiply 20 times 2. Force is 20 times the displacement of 2 would be 40 joules, and that equivalent would be the area in this rectangle. It's a 20 up and 2 over rectangle. But in this case, the force is increasing. It's not a constant. So we can't look at the whole rectangle. We just need to look at what's underneath of this plot. It's the area under there. To find the work done by a spring, that'll be Ws. There's an integral, and instead of f of x, we're going to plug in k delta x, or kx, because that's the value that's going to be changing. K is a constant, x is what's changing, dx. That denotes x is going to be what's changing. We're going to take that from 0 to a position of 2 meters, 0 to 2. All right, let's integrate. Integral of kx dx is going to be k as a constant, x squared over 2. I'm integrating, so I don't need the sign anymore. Kx squared over 2. We're going to take that from 0 to 2 meters away. And so as you see here, there's a value coming out of this, k 1/2 kx squared. That'll pop up later on when we talk about potential energy of a spring. But as for now, we can plug in our k value of 20, and x, our final value of x is 2. Don't forget divided by 2, minus 20 times our initial value of x, 0. And there it is. 20 times 4 is 80, divided by 2 is 40 joules. All right. So that's the work done by a changing force. And finally, this brings up a few scenarios where force is not going to be constant. So I'd like to just give you a couple just to try out and to think about. What if our force displacement function is a parabola? Or what if it's a, doesn't have to be a spring. What if it's just a straight line? Or what if we have something like this that changes? Okay, so what are you doing in these cases? What's the total work done? That's what we'd be finding out. You just be looking for, work done. You need a beginning and an end. So what's the work done between 0 and, let's say, 5 meters? We'd go up here and denote that this is a parabola. It probably has some kind of function like force equals, starts at 0. So why don't we just say like 2x squared? Okay, so you would integrate from 0 to 5 meters, 2x squared, and that would give you the area underneath. What about this kind of scenario? Well, we're going from, let's say, 0 to 5 again. 5's right there. Take whatever that force is. You'd have to know that. It might be like that 20 newtons or something like that. And just find the area underneath here. And for something like this, you'd probably need to know a little bit about where these changes happen at these positions. Maybe this is 2, 4, and 6 meters, and we get up to 8. This might be at 10 newtons. That would be 20. So this one might be about 25. So with values on that graph, you could add up the area in here plus the, what's the area in here? You might be able to divide that up into a little bit of a triangle, get some area there. We get a little rectangle down here. And here's a bigger rectangle. This is a 2 by 25 rectangle. So there's 50 joules represented right in there. And what would this be? This would be half of 50 joules. That would be 25 joules in there. And so you just add up like the little sections, whatever they would turn out to be. That would be 25. This little piece here would be 20. So that means this piece would be 20. And this one would be, let's see, that's 10 to 25 is 15. Times 2 is 30, but this is a triangle, so it's half of that. So it's down to 15. So if we added up all that area in there, that would be the total work in joules. 20 plus 20 is 40, plus 50 is 90. That would be 115 and 130, if I did all that summation correctly. So it'd be about 130 joules of work. So that's what you can do with this. Just things to look out for when you're dealing with force and displacement. If you ever get a scenario with force and displacement, think, oh, maybe work's involved. I can figure out a change in kinetic energy. I can find a final velocity. We're talking about lifting things up. I can find out how high it's lifted up. All right, so that's about it on work. It's a big introduction, the work and work kinetic energy theorem. You'll see all these things working together. No pun intended. But I hope this does all work for you. Take care.